All right, so we spent some time now. We're essentially just over halfway through this course, but we've covered kinematics and dynamics and energy and impulse and momentum. And Unit 5, actually in the scope and sequence of our book, comes right after Unit 2. But we save it for second semester because Unit 5 is a nice little review of some of the things that we've already learned. We've talked about kinematics, which are which are the study of motion and using XF and XI and all that we talked about right at the beginning of the year. Then we talked about dynamics, which was using forces to solve for acceleration. And now rotational motion is actually going to combine these two topics into one topic for things going in a circle. Everything before we treated as a quote-unquote particle, so we used the particle model, and a couple times we examined how this particle model isn't necessarily correct. If you remember, we talked about the ring versus the disk, and that'll come up a lot this unit. But so this is like a nice little review of these two topics, but we're going to be talking about things going in circles. So here we go. And we're going to start with a rotational motion video. So in this video, it's actually really cool. He's got like this little van or school bus, and it rides around on the record and plays the record. But we can use this concept, an object just going around in a circle, to get into rotational motion, because that's going to bring up a few newer or different ways of our concepts that we've talked about before, different ways of explaining those concepts. So we'll take a look at that in this section. So the first section is getting into describing circular and rotational motion. Now, we did get a quick little introduction to this in chapter 6 at the end of Unit 2, when we got specifically into uniform circular motion. And some of these concepts from uniform circular motion are going to come back right now, but at the same time, a lot of them are going to get tweaked a little bit, because now we're going to go ahead and get rid of that uniform as we talk about this rotational motion. Okay, so the first question is, what is rotational motion? And rotational motion is it's the study of the motion of any object that spins about an axis. So here we have a windmill, and it's always spinning around this center axis. And one of the examples that I'll use a ton in class is we have a bicycle wheel, and we've seen that bicycle wheel before. Remember, we did the gyroscope demonstration when we talked about momentum last unit. But it's anything that spins about a central axis. And that can be expanded a little bit. This right here is just a fan blade or a windmill blade, but we'll get even different types of examples for that as well. So in order to do this, we need to build a little bit of background about angular position and angular velocity and all that kind of stuff. So before, we used variables like xf and xi to describe it, and we use those in terms of meters. Well, that's not going to work so much for us anymore. Now we're going to talk about some angular stuff. And at the bottom here, I have a little path, right? And if I were to start right here and go this distance, right, one particle as it rotates about this distance, we're going to describe it in terms of a couple different things. So first off, we use the angle theta. And theta is going to reference where we started. This is our 0 spot right here, but theta is going to represent the distance that we travel, but not necessarily the distance that we travel, but the particle's location from the 0 point. And we'll use that in theta. And we'll talk more about that in just a little bit, but theta is positive when it's counterclockwise. So positive direction is counterclockwise, and the negative direction is clockwise. And that might seem weird, but we actually, a way to remember that is by thinking about the right-hand rule for torque. The right-hand rule for torque states that if you take your hand and you curl your fingers in the direction of the object's spinning, then your thumb will point in the direction of the torque. And you think about like, this might be hard to visualize, but if I like screw something into a wall, I turn my fingers, if my thumb is pointing towards the wall, I turn my fingers clockwise, and that's where we get righty-tighty, lefty-loosey. But if I hold them straight in front of me and I spin my fingers counterclockwise, then my thumb is pointed up, and that's how I get that positive direction. But I'll explain that a little bit better in class. Okay, so back to this theta thing. So theta is actually measured in radians. Now, not degrees. Now, we've used degrees a ton for a few different purposes, right? We've used degrees for when we talk about angles of incline, stuff like that. But now, when we're going in rotational motion, theta is actually measured in radians. And we just abbreviate that rad. So like, we got 2 rad, because that's me, 2 rad. So we use radians to describe that. Now, an important note is that even though we have radians right now, our calculators are still going to be in degrees. We will, in this class, never ever have our calculators in radians. We're only ever going to have them in degrees. The only time it actually matters is trig functions, which we're not going to do trig functions of radians right now, so we don't have to worry about that. The last thing is on the last slide, I said, well, if we start from here and go to here, we travel some distance, and that's something we would have talked about more in Unit 1, but we call that distance the arc length. So it travels some distance, arc length. I do have a formula for arc length, and that is that the arc length is the radius of however far you away are from the center times your angle, or times your angular displacement, or angle in radians, and that is a physical distance. If I go back to a couple different math classes, then we know that 1 full circle is 2 pi radians, and I can also prove that here, because 1 full circle, the distance I travel is 2 pi r. And if I go back to dividing it by r, because the angular displacement is the arc length divided by the radius, I get 2 pi rad. So it does actually work out that way too. Okay, so now we got to get into concepts of things that we talked about in first unit, such as displacement and velocity, but we're going to add the term angular in front of it because we're now talking about rotational motion. So I have 2 pictures down here. There's this guy on the left and this guy on the right. And when we talked about linear motion, a particle that traveled fast meant it had a greater displacement in some time interval. So as I look at these 2 on the bottom, this one goes about 1/4 of a circle, and this one goes about 1/2 a circle. So I can say that this particle over here, it undergoes a greater angular displacement every second, and therefore it has a greater angular velocity. So it's not completely new concepts. It's extremely similar to things that we talked about in Unit 1, but angular velocity is the angular displacement that the particle moves every second. So here's my formula then for angular velocity, and we use the Greek letter lowercase omega to describe angular velocity, and that's just our angular displacement over time. This is back to the theta that we talked about just a couple minutes ago and our time interval. So the angular velocity of any object going in circular motion isn't going to change. But we're also going to talk about in future sections, we're going to talk about when it does change. All right, so we got a quick little example, and obviously we'll do this in class, but as we're looking at these 2 different objects, this is just the same picture from the last slide, but which one we're determining their angular velocities. And you notice that we have absolutely, except for the time interval, no numbers here. But angular velocity is a concept that doesn't rely on a physical coordinate system. So before we did velocity, right, was displacement over time, and now that's not this displacement thing, which was measured in meters. Now we're going to be using radians, which it doesn't matter how big your circle is, you're going to get some type of angular velocity. So we'll take a look at that problem in class. Or, well, here are the examples, but anyway. Okay, so angular displacement and angular velocity. So back before we had linear displacement, and we said that was our delta x, and now we have angular displacement. That's our delta theta. That was our final position minus our initial position, and that will stay being true. Or it was velocity times time, and now it's angular velocity times time. So anything in uniform, and again, this is uniform circular motion, which, if you recall, when we talked about this initially in Unit 1, we had uniform motion, which was no acceleration, and then we had non-uniform, which had acceleration. And that concept is going to stay true for this. So this is like the constant velocity version of uniform motion, except now in angular or rotational motion. So those concepts that we talked about way back at the beginning of the year are still going to stay true for this. Now, there is another way we can also talk about angular velocity, and that's with a couple concepts that we did address in uniform circular motion. Now, if you recall, back in uniform circular motion, we had this concept of frequency, which we used the letter F for, and we talked about period, which we used the letter T for. Now, the period was how long it took to make one revolution, and the frequency was the inverse of that. It was the number of revolutions per second, aka the frequency or the hertz of that motion. So we can still use these concepts, and we actually did use these in Chapter 6, but this is a nice little review. Remember that velocity is distance over time. So that means that angular velocity right here, we have the distance, which is 2 pi rad, which is one full circle, divided by the period, which is the time for one full circle. And of course, we talked about frequency is inversely related to the period. So we get the angular velocity is also 2 pi rad times the frequency. I got a little quick check here just to incorporate those couple things. Here we have a ball rolls around a circular track with an angular velocity of 4 pi radians per second. What's the period of the motion? Well, if it's 4 pi radians per second and one circle is 2 pi, that means that this is going around the circle twice every second, aka it has 2 hertz. Well, 2 hertz means that it only takes a half a second to go around one time. And again, this is inversely related. Frequency is 1 over the period, so I can do 1 over 2 and get a half of a second. All right, here's a partner problem that you'll take a look at in class. It says that the crankshaft in your engine is 3,000 RPMs. What's its angular speed? And we'll take a look at some conversion factors and thinking that, well, 3,000 RPMs, that's 3,000 revs in 1 minute. So we got to think about this rev thing because we don't use revs in our calculation, but we'll see it all the time. So one of the first steps we're going to do with a lot of these problems is convert not only 1 minute into 60 seconds, but also 1 rev is 2 pi rad. And we'll use this conversion factor to get our answer in radians per second, and we'll take a look at that more in depth in class. Here is that problem worked out. As you can see, the first thing is to get it to revolutions per second, aka that's our frequency, and then we can use this formula, the 2 pi rad times the frequency, to figure out that it's traveling at 314 radians per second. Okay, so way back at the beginning of the year, we looked a lot. We spent a ton of time looking at graphs. And we started with the graph of position versus time. And we took the slope of that graph and we came up with our next graph of velocity versus time. Then we took the slope of that graph and we came up with the graph of acceleration versus time. Then we also talked about the area under the curve, and the area under the curve of a velocity versus time graph, of an acceleration versus time graph, is going to be our change in whatever the previous graph is. So in this case, it's the change in velocity. And then the area under the curve of the velocity versus time graph is going to be our change in position, aka our displacement. So we have position versus time, we had velocity versus time, and we had acceleration versus time, change in velocity, change in position. All of these graphs are still true, except now we put the word angular in front of them. We have angular position versus time graphs, angular velocity versus time graphs, and those can be in revolutions per second, revolutions per minute, radians per second. It doesn't matter. All of these things are good to go. They're ways of showing graphically showing motion. All right, one last little thing. There is a way, so angular velocity talks about going in a circle, linear velocity talks about going in a straight line. But if I am a dot on here going in a circle, at every single point I have some instantaneous velocity. And this formula right here, V equals omega r, is a way of telling me that if I'm this point, how fast I'm going. And that's just the angular velocity. So remember, that's the omega is angular velocity, and r is just the radius. So depending on the radius away, the faster I'm going. And this is a nice way of thinking then, or a nice way of relating those two concepts. Here is a partner problem. It's taking a look at 2 points on a CD-ROM. And again, this gives us information in revolutions per minute. So the first thing I have to do is, well, if that's revolutions per minute, I want to get stuff into 1 minute, into 60 seconds, and of course, 1 rev into 2 pi rad. But this problem is going to say, okay, well, how do we get our velocities of these 2 points? And the first step is to get the angular velocity, which is what I was just doing here. And the second step is to get the linear velocities of each of the 2 points by the formula that we were just discussing in the previous slide. So I can go through and work through those, and you would come up with 2 velocities. As it is shown in the picture, velocity of B, as you can see from right here, it's got twice the radius. It ends up having twice the velocity. So I always ask this question: if you're on a merry-go-round and you're afraid of going fast, where should you sit? You should sit towards the middle, because if you look at the circumference of this circle, that's its path that it follows. The B's path follows a much larger circumference, but it does so in the same amount of time. And remember, velocity is just distance over time. So therefore, B has to be going much, 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 much faster. All right, we got a quick check here. What's the angular velocity? This is an angular velocity. How many revolutions does the wheel make in the first 4 seconds? Well, if this is velocity versus time, I'm technically looking for displacement. So I'm going to chunk this graph up. This is 1/2 2 times 2, so this is 2 right here. This is 4 right here. And what's my unit? Well, this is revolutions per second times a second. So my answer is revolutions. So my answer is 6 revolutions in the first 4 seconds. Another quick check. Starting from rest, a wheel with constant angular acceleration turns through an angle of 25 rad in time t. Through what angle it turned in 2t? A lot of you will jump to 50 rad. Sorry, that's incorrect. And the reason is we're doubling the time, but this is a constant acceleration problem. So when we did constant acceleration before, we said xf equals xi plus vi delta t plus 1/2 a delta t squared. Well, now, very similarly, I have theta f equals theta I plus omega I delta t plus 1/2 alpha delta t squared, and I can see that theta f is directly proportional to this guy right here, delta t squared. So if I double the time, I will quadruple the angular displacement. And that's actually going to finish us up for this section. We're going to dive more into this rotational motion, quantifying it, talking about the angular acceleration, where it comes from, and that's all part of this chapter. So we'll see you in the next segment.